Alright everybody, welcome back. We are talking about section 7.4 of AP Calculus in this video, reasoning using slope fields. Basically in this lesson, all we're going to do is we're going to go through a few examples related to slope fields, some questions that we might answer, and we're going to talk about some of the reasoning that might occur when we encounter a slope field problem, like one of these. Alright, I would recommend during this video that, you look at the introduction to the example and then pause the video and see if you can figure out what the answer is and what your reasoning is for any of these problems. And then start the video back up and see how you do. Alright? Example 1. One of these slope fields is for the differential equation dy dx equals x plus y, and the other is for the differential equation dy dx equals x minus y. Identify which of the slope fields represents each differential equation, and explain how you chose your answer. Alright, so go ahead and pause now, try and determine which one is which, and how you made that determination. And I'll be back with you in a few seconds. Alright, now looking at this problem and thinking about this problem, I think about points along the diagonal y equals x. And what should happen to points along those diagonals for the two different differential equations? For this differential equation, every point along the diagonal y equals x should have a slope of 0. So dy dx equals 0 for y equals x. Whereas for this slope field, dy dx equals 2x or 2y for all the points on the line y equals x. And so for one of these slope fields along that diagonal, the slope lines should be getting steeper and steeper. For the other one, they should stay the same, close to 0. And if I look along this line, this one, it looks like the slope lines get steeper and steeper as we move from left to right along that diagonal. For this one, it looks like the slope lines stay the same as we move from left to right along that diagonal. And so I believe that this is the slope field for dy dx equals x minus y, and this is the slope field for dy dx equals x plus y. And you've heard my explanation. We can also look along the diagonal y equals negative x. This graph should exhibit, along that diagonal, should exhibit the behavior where the slopes are 0, and it looks like it does. Okay, so that's our first example. Example 2. The slope field for a certain differential equation is shown below. Which of the following could be a solution to the differential equation with the initial condition y of 0 equals 0? Okay, so go ahead and pause now and see if you can figure out which one is which. And I'll be back with you in a few seconds. Alright, so first of all, which of these could be a solution to the differential equation with the initial condition y of 0 equals 0? So if I substitute 0 into each of these for x, I should get 0 for y if it's a possible solution. If I substitute 0 in here, I get 0 over negative 4, that is 0, so that passes the initial condition test. If I substitute 0 in here for x, then y is e squared. E squared is not equal to 0, so I can eliminate this one. Eliminate with initial condition without even looking at the slope field. If I put 0 into c for x, I get 0 for y. And if I put 0 into d for x, I also get 0 for y. So a, c, and d pass the initial condition, but b does not. Alright, now let's look at the slope field. So, looking at the slope field, the first thing that jumps out to me when I look at this slope field is that the function is undefined, or that the slope is undefined at x equals negative 2, which means that at x equals -2, all of these denominators should be 0. That's true for choice D. It's true for choice C. It's also true for choice A. The thing about choice A, though, is there's another x value for which that denominator is 0, where we should see undefined behavior if this is the right slope field. And so we look at this, and at x equals 2, I should have undefined behavior if choice A is my answer. But it's not, so I can eliminate this. Eliminate slope not undefined at x equals 2. So that narrows it down to 2 options. I'm going to go ahead and look at C next. Choice C matches the asymptote there. And then I need to think about what's the behavior of the tangent function like. And you know, the tangent function has all these asymptotes in predictable moments. This would say that the slope field should have an asymptote, or undefined slope at x equals pi over 2, since that is where the slope or the value of the tangent of x is undefined at x equals pi over 2. And we look at pi over 2, which is about 1.5 and change, and we see no evidence of an undefined slope pattern there. So I'm going to eliminate this one, which leaves us with D as our answer choice. All right, let's go on to example 3. Consider the differential equation dy dx equals quantity x plus 1 over y and its slope field shown below. Describe all points in the xy plane, y not equal to 0, for which dy dx equals -1. Okay, go ahead and pause the video and see if you can figure out the answer to this one, and I'll be back with you in a few seconds. All right, so the first thing I did here in this problem was I looked at the slope field and I went, okay, let's see, where are the slope lines -1? And I find them right here. So it appears that all of those slope lines with a slope of -1 are on the same line. And so we can describe all the points in the plane where y doesn't equal 0, so everything except for where that hole is in the graph, for which dy dx equals -1. Now how do we describe those? Well, I'm going to set dy dx equal to -1, and if I solve this equation, I can say that all points in the xy plane for which dy dx equals 1, all points are on the line y equals -x minus 1. Ta-da! All right, example 4. One of the following slope fields is the slope field for the differential equation dy dx equals sine of xy, and the others for the differential equation dy dx equals cosine, the quantity xy. Which slope field represents which differential equation? Explain how you determined your answer. All right, go ahead and pause, see if you can figure out the answer to that one, and then I'll be back with you in a few seconds. All right, I'm back. The key in this one, to me, is the behavior along the axes. Whenever x is 0 or y is 0. Because whenever x is 0 or y is 0, that makes what's inside of the sine function or cosine function equal to 0. Sine of 0 is 0, but cosine of 0 is 1. And so this one should have slope lines with a slope of 0 along the axes, and this one should have slope lines with a slope of 1 along the axes. And we can clearly see that this one has slope lines with 0, so this is going to be dy dx equals sine of the quantity xy. And this one has slope lines with a slope of 1 along the x and y axis. So this is going to be dy dx equals cosine of xy. And the last one, example 5. Explain why the following could not be a slope field for the differential equation dy dt equals negative 0.3y. So think about it. If we put, hey, let me give you some time. Go ahead, pause your video, think about this for a few seconds, and then I'll be back with you momentarily to go ahead and go through the answer to this one. All right, I am back. Now, the first thing I'm thinking about when I see this differential equation, dy dt equals negative 0.3y, the slope lines are dependent on the value of y. And since we're in the first quadrant, all the y values are positive, and so this slope field should have negative slopes at every single point in this picture. And it appears that it does. So that's not a way to differentiate this, to make our determination. The other thing, though, is that since only y is in my differential equation, that means that I should see horizontal slope patterns. For instance, if I pick a value of y, if I look at all those slopes along that horizontal line, they should all be the same since the slope field is dependent on the variable y, and they're not. And so that is how I can tell this is not the slope field. For a given value of y, all of the values of dy dt would be the same, which causes a horizontal pattern in slope field. Pattern in dy dt slope field. This slope field does not possess a horizontal pattern. All right, very good. That brings us to the end of our video, the end of section 7.4. Depending on which class you're taking, that'll dictate where we go next. We're either going to 7.5 for those of you who are in BC, which is Euler's method, or for those of you who are in AB, you should jump ahead to section 7.6. Finding general solutions using separation of variables. All right, that brings us to the end of this lesson. Have a great rest of your day, everybody, and we'll see you next time. Bye-bye.